Well, thank you very much for the kind introduction, Jim, and it's a pleasure to be back in your forum. I still remember my trip 2 years ago to Ireland fondly, and I thought another opportunity to speak would be a nice excuse to see your beautiful country. Today I'm going to be speaking about work that I did with Will Happer. Will said, William, you don't need to put my name on the presentation since you're giving it. So if there's something unclear, that's my responsibility. But if there's something that looks very nice, please recognize that this is the result of a very fruitful collaboration. Let's start to slide 2. So first I'd like to talk about the concentration measurements of methane versus time. And these come primarily from ice core data. So on the left upper picture, you see a scientist in Antarctica and he's drilling to get an ice core. In practice, you can get very long ice cores, such as shown in the picture on the right. And if you look carefully, you see this dark ring in that ice core, and that's the result of a volcanic eruption. So all that snow gets embedded in the ice. Next year, there's presumably no volcano, and then you get clear ice. So you get a series of layers analogous to tree rings, and you can count back in time. In addition, in the ice, you have trapped air bubbles, and you can look at the concentration of methane in these air bubbles to get a estimate of the methane concentration going back hundreds, even thousands of years. And the result is shown in the graph below. So the black curve is the methane concentration. In 1880, it was about 800 parts per billion. Throughout the 20th century, you see it has increased to the present day about 1,800 parts per billion or 1.8 parts per million. What I thought was interesting is if you look at the derivative or the growth rate of that curve, we get the red graph. And you see that methane started to increase suddenly around 1905. Then around 1950, it increased until 1980. And then after 1980, some real weird things happened. The growth rate decreased sharply. In fact, in a few years after 2000, it was negative. So methane was declining in the atmosphere. Now, the obvious question to ask is why? What happened after about 1990? And I know a number of people, including myself, have asked this question. And the only answer that I've gotten is that communism ended in Russia. That meant that the natural gas pipelines that were leaking very badly under communism were given superior Western technology and the leakage stopped. Therefore, the growth rate in methane decreased sharply. That has a bit of a ring of Western superiority to it, and I am a little troubled by it. Of course, you could go back and say what happened in 1905 and blame that on the first attempt at a Russian revolution, the recalling of the Duma, but I'm a bit suspicious. I have never seen a paper that actually made some quantitative measurements of the natural gas or methane loss from leaky pipelines in Russia. And if someone could illuminate that for me, I would greatly appreciate it. So methane has increased, but the growth rate is a bit unclear, especially in the last 2 decades. Now, if you look at the Earth, it has a finite temperature. The average temperature of the Earth's surface is about 15 Celsius or about 288 Kelvin. So you just add 273 to Celsius to get the Kelvin temperature. Every object radiates heat. And we like to think of this heat as just infrared radiation as opposed to visible radiation that we see with our eye. Now, we will be looking at 5 greenhouse gases: H2O, water vapor, carbon dioxide, CO2, ozone, O3, nitrous oxide, N2O, and of course, methane, CH4. The definition of a greenhouse gas is they transmit sunlight, visible radiation, but they absorb at various infrared colors or frequencies. Now, what we do is we calculate the transmission of infrared radiation or heat through the atmosphere to outer space. So I thought this was a rather nice picture. You see the Earth, you see this blue haze. That's the atmosphere that we are considering. Slide 4. So the first thing I'd like to discuss is the altitude dependence of the temperature and also the greenhouse gas concentrations. So on the left, we see a graph of temperature on the horizontal axis versus altitude on the vertical. At the surface, we're at a temperature of 15 Celsius or 288 Kelvin. As we increase in altitude through the troposphere, the temperature decreases. Then as you get into the stratosphere, the temperature goes up. The reason for that is there's an ozone layer. Ozone absorbs this ultraviolet light from the sun and it heats the surrounding air. So the temperature goes up in the stratosphere, and then in the mesosphere, the temperature starts to go down. The density of air is very low, and the temperature continues to go down until you get to what we call the top of the atmosphere at about 86 kilometers. On the right-hand side, you see the concentrations of the greenhouse gases. So the horizontal axis is labeled in parts per million. So water, the blue curve, at the surface we have about close to 10,000 parts per million. And as you go up a few kilometers, the water concentration decreases sharply. In contrast, CO2, it remains at about 400 parts per million at all altitudes. Then we come to the dashed black curve, which is methane. It starts out at the surface at about 1.8 parts per million, and it decreases as you go in high altitude. Interestingly, when you go to high altitudes, some of the methane molecules sometimes react with ozone to produce two water vapor molecules. So methane in the stratosphere is a source of water vapor, which is a powerful greenhouse gas. The green curve is N2O. It starts out at 0.32 parts per million at the surface and decreases as you go up. And then finally, we have ozone. Its concentration is relatively low at the surface, but maximizes about at 35 kilometers. So in our calculations, we take into account the variation of the concentrations with altitude. Slide 5. So what this graph shows is the various transitions or infrared colors or frequencies that each of these gases absorb light at. So the horizontal axis you can think of infrared color. Scientists like to use the word frequency. In this field, they measure frequency in units of inverse wave number. Typically, I remember in my education, I was taught frequency is measured in hertz. To convert from wave number to hertz, just multiply by the speed of light. Each of these 5 graphs have a black curve, and that corresponds to the distribution of infrared light emitted by a surface at 15 Celsius. So this is known as the Planck blackbody curve. So you see that the black curve maximizes at an infrared frequency of about 600 wave numbers. Now let's look at the top curve for water vapor. The blue dots, each blue dot corresponds to one of these infrared lines that we consider in our calculation. And you see there are thousands of these blue dots. Many of them are located from 0 to 500 wave numbers, where you see that the Planck, that black curve, is very significant. There are also many more around 1500 going on to 2000 wave numbers. When you get out to those high frequencies, the black body curve is relatively small, so you don't have much heat being absorbed by the water vapor at those high frequencies. Next, let's look at CO2. Notice that the CO2 has a lot of lines around 650 wave numbers, and this is very close to where that black line has its maximum. And that is why CO2 is so very important when you talk about global warming. It also has some transitions around 2300 wave numbers. Those are not very important because not much heat is produced by that black curve. Third, we consider ozone. Notice that ozone also has some transitions around 650 wave numbers, but since there is a lot less ozone than CO2, those transitions are not that important. However, around 1018 wave numbers, we have a lot of ozone lines where we do not have many CO2 and H2O lines. So you can expect those lines at 1018 wave numbers to be very important. And finally, we have N2O and methane. N2O and methane have a lot of transitions around 1300 wave numbers, and that's significant. Their wavelength, the frequencies that those two molecules absorb are going to strongly overlap. So if you want to look at the effect of methane, you definitely have to know N2O. You also have to consider water vapor, which also has a lot of transitions that overlap with those N2O and methane transitions around 1300 wave numbers. Slide 6. One of the ways that people get measurements of the high atmosphere is they have a balloon. So here I got a picture of one. This is a balloon that can go to very high altitudes, about 40 kilometers. There is then an instrument that hangs from the bottom of the balloon. In that balloon package, you can put something known as a spectrometer that can look at the intensity of infrared light measured versus frequency. And when people did this experiment, they got data shown at the lower left. And I refer you to that gray curve, which is the measured data. So here we're looking at intensity of the radiation produced by primarily CO2 molecules that absorb in this range from 550 to 800 wave numbers. Now, when people get data like this, they want to understand it. And for the technical experts here, they like to fit it using a so-called Voigt line shape. This is if you don't understand this, you can just not pay attention for a minute. A Voigt line shape is just the convolution of a Lorentzian with a Gaussian distribution because the molecules are moving. The important point I want to emphasize is that this black curve doesn't fit the data very well when you get out to the edges of that absorption band around 500 to 550 and 750 to 800 wave numbers. The reason is that the line shape is not well fit by a Voigt line shape. You have to worry about collisions, and collisions have the effect of truncating that line shape. So over on the right-hand side are results of our model calculations. The black is when we consider a Voigt line shape, which closely resembles the curve at left. Blue is when we truncate the line shape when we do a better job. And you notice the blue curve much more closely resembles the experimental data. So the point here is you can have a modeler. They are very conscientious, but they always have to check their model results to experiment. And that's something we like to emphasize. Slide 7. So what we show here is 4 different infrared colors, and we plot the heat on the horizontal axis, or the flux, versus the altitude on the vertical axis. So in the left column, we consider an infrared frequency of 500 wave numbers. Now this is at a frequency where there are a lot of water lines. And sure enough, if you look at the infrared heat at the surface, it increases as you go up a few kilometers. And then when you go up a few kilometers, there's very little water vapor. Your heat is no longer absorbed and it just goes straight to outer space. In contrast, if you look at the second graph, part B, here we consider a particle of light known as a photon at 667 wave numbers. This is at the center where CO2, carbon dioxide, likes to absorb. And notice it's very difficult for your heat to leave the surface. The heat has virtually zero flux until you get to very high in the atmosphere, about 86 kilometers. Only then is the atmosphere thin enough, the density low enough, that you can escape the Earth. Part C shows a photon at frequency 971 wave numbers. None of these gases that we've talked about, CO2, water vapor, ozone, etc., absorb that color. So you can nicely escape the Earth. The Earth's atmosphere is transparent at that frequency. Finally, in part D, we consider a frequency of 1,016 wave numbers. This is where ozone absorbs strongly. And sure enough, if you look at the upwards heat or flux, it goes down when you enter that ozone layer at about 35 kilometers, and then only increases when you go higher. Slide 8. So now let's look at what we see in terms of the heat at the top of the atmosphere versus the frequency. First, we're going to pay attention to the top graph, which illustrates the effect of carbon dioxide. The blue curve considers the case of a transparent atmosphere. So if we had no greenhouse gases, we just get that nice Planck black body curve corresponding to a surface temperature of 15 Celsius. Now we add in our water vapor, our CO2, ozone, N2O, and methane. And then you get the black curve. So notice from 0 to 500 wave numbers, the black curve is lower than the blue curve. This is due to absorption by water vapor. And then at 650 wave numbers, we see this big decrease, this big well, that's the CO2 absorption. Then at about 1,018 wave numbers, we see the big ozone absorption. From about 1,300 to 1,700 wave numbers, we see also a lot of absorption. It's mainly water vapor, but there is also some methane and N2O. Now we say, well, let's turn off the CO2. So we say, let's plug in CO2 of 0 parts per million. No CO2 in the atmosphere. Then instead of the black curve, you see the green curve. So again, you see that CO2 big dip at 650 wave numbers very well. What happens if we double CO2 to 800 parts per million? Then you get the red curve. So the difference between the red curve and the black curve, and yes, they overlap almost entirely, but there is a difference. That's what the global warming fuss is all about. Next, let's go to the lower curve where we look at the effect of methane. The blue curve is the same as in the upper curve. That corresponds to a transparent atmosphere with no greenhouse gases. Then the black curve is the same as the upper curve. But now we're going to consider a green curve where we turn off our methane, and a red curve where we double the methane concentration. And you have to look carefully at about 1,300 wave numbers to see any difference at all. So I think you probably understand now why I wanted to begin the discussion with CO2, because if I had begun with a lower curve, you would have said, William, we don't see any effect. Well, there is an effect, but it's small. Slide 9. Well, the question you can have is, William, those are nice curves, but how do you know they're right? So let's look at some satellite observations. These are observations made by the Nimbus satellite. The picture is shown at the left. This was a satellite that operated in the early 1970s. So this satellite looked at the heat flux in this frequency range from 400 to 1600 wave numbers. For technical experts, this was a Michelson interferometer. Now, on the right-hand side, we have the observations. On the upper right, we see the observations of heat flux versus frequency when the satellite looked at the Sahara Desert. In the middle, we see the Mediterranean observations, and down below, the Antarctic observations. I first like to draw your attention to the vertical axis, which you can think is a measure of heat. For the Sahara, the heat, that intensity measurement goes from 0 to 200. For the Mediterranean, the vertical axis goes from 0 to 150. For Antarctica, 0 to 60. That, of course, makes sense. Hotter objects produce more heat than cooler objects. Now, we have taken our model, put in the CO2 concentration back in 1970, estimated the surface temperature of the Sahara, and calculated what that data should look like. And if you look at the Sahara model and the Sahara observations, the two seem to agree rather well, in fact, extremely well. Similarly for the Mediterranean. Now for Antarctica, it's kind of interesting. The red curve, that corresponds to the distribution of heat that you would expect the surface to produce. So what we see in Antarctica, unlike for the Sahara and the Mediterranean, is that more heat is produced than what you would expect for a surface at that temperature. And the obvious question to ask is, why? It turns out when you are at the South Pole and you stick your hand up, or maybe you go up a little higher, a kilometer or so, the temperature does not decrease as it does in the Mediterranean or the Sahara. It goes up. There is a temperature inversion. The reason for that is the South Pole is at a high altitude. There's very cold air sinks. So if you have hotter air up at higher altitude, this acts as a much better radiator than colder air. And that's why you get more radiation produced than you would expect given the surface temperature of Antarctica. Let me go back first to slide 8. So here we had shown in the upper diagram a plot of our heat flux versus frequency on the horizontal axis. What we're now going to do is we're going to integrate or add the heat at all the different frequencies. And that's what is shown in figure 10. So on the horizontal axis, we have our heat where we've summed over all the frequencies. And on our vertical axis, we plot the altitude. So as you go to higher altitude, the net heat going up increases. The green curve corresponds to 400 parts CO2, our present atmosphere. Our atmosphere also having the water vapor, ozone, methane, and N2O. That dashed black curve, that would be the heat flux if you did not have any greenhouse gases. So as you would expect, it's just a constant straight line. Next, we have plotted two additional curves. One is the curve if we double CO2 concentration to 800 parts per million. And we see that green curve has now shifted a bit left. It's harder for the heat to escape the Earth's atmosphere. For fun, we've also said, what if we cut the CO2 in half to 200 parts per million, and you see the green curve is now shifted to the right. It's easier for heat to escape. Now, what we're going to be talking a bit about is something called the forcing, which is just defined to be the difference from the green to the red curve. What happens to the heat flux when you double the CO2 concentration? Now, to do that, I have to talk about something called saturation. And what is saturation? Well, the best definition that I have heard is one that Will came up with. He said, if I take a barn, and it's not been painted in years, and if I give it one coat of red paint or a second coat, I can sure tell the difference. But if I give it 10 or 11 coats, I can't tell the difference between the 10th and 11th coat. That's an example of saturation. So what we show in the graph here is forcing plotted on the vertical axis, so you can think of this as the amount of heat, versus the change in the greenhouse gas concentration on the horizontal axis. So 0 here means no greenhouse gas. 1 means our present day greenhouse gas concentration. So in the case of CO2, 1 means 400 parts per million. 2 means you double the greenhouse gas. So in CO2, it means 800 parts per million. So if you have no greenhouse gas, where you're at 0, and you slightly increase the amount of greenhouse gas, you see these forcing curves increase very dramatically. In the case of water, it goes from -60 to about -10 when you go from 0 to 0.5 on the horizontal axis. But when you get to the higher values from, say, 1, which corresponds to 400 parts per million CO2, going up to, say, 800 parts per million of CO2, where it's the fractional change is 2, you see that things flatten out, things saturate. So the point I want to emphasize is that all these greenhouse gases are strongly saturated, especially water vapor and CO2. Now for the next slide or two, I have to apologize. I'm going to be a bit technical, so I'm sorry if I lose you. So what we like to define is we take this heat flux, which is measured in watts per square meter, and if we divide by the greenhouse gas column density, so this is the number of molecules per square meter, we get a unit of power, which we call the power per molecule. So let's see what this graph means. First, let's look at the left side where we consider H2O, water vapor. First, we're going to do an experiment where we have an atmosphere that has no greenhouse gas at all. We now add 1 molecule of water, a second molecule. We measure the heat flux divided by that column density, and we get that blue line, that very low density water vapor power per molecule. Next, we repeat the experiment. But now, before adding 1 molecule of water vapor at a time, we add in 400 parts per million CO2, we add in the ozone, we add in the N2O and the methane. Now we add in 1 molecule of water, another molecule of water. Measure the heat flux divided by the water column density, and then you get the green line. And notice we get for water vapor virtually the same. The green and the blue lines nearly overlap. The reason for that is the water vapor lines, frequencies that water vapor absorbs at, do not overlap strongly with those other 4 greenhouse gases. Finally, we do the experiment a third time. We take our empty atmosphere, and now we load in our water vapor at about 10,000 parts per million, our CO2, our ozone, our N2O methane. And now we add one additional water molecule, a second additional water molecule. We measure the heat flux divided by the column density, and then we get that red line. And now you see there's a huge difference between the blue and the red, and that gives you your measurement of the saturation. That scale on the left side is logarithmic. That means that each unit changes by a factor of 10. So you see the saturation is about a factor of 1,000 for water vapor. Next, we move over to CO2. We do those 3 experiments again, and sure enough, you see a big difference between the red and the blue lines, indicating that CO2 is very strongly saturated. Then we go to ozone. Ozone, there is quite a difference between the blue and the red lines, a factor of 10. It's saturated, but not as much as CO2 or water vapor. The simple reason is there's a lot less ozone in the atmosphere than either CO2 or water vapor. And the same is true for N2O and methane. In the case of N2O and methane, you notice that the blue and the green lines, they are quite separated. And the reason is that the N2O and the methane, they like to absorb similar frequencies or infrared colors. Slide 13. Now, I'm sure all of you, when you go home and you talk to your children or your grandparents, you don't really want to tell them about flux or heat. You want to talk about temperature change. That's something everyone understands. So let's see if we can estimate what is the temperature change due to doubling CO2. So on the lower right, what we have plotted is that heat flux on the horizontal axis versus altitude on the vertical axis. And you see when we double our heat flux, double our CO2, sorry, the heat flux shifts quite dramatically, about 3 watts per square meter at the top of the atmosphere. What then happens? Well, we have to understand a little bit about how energy is transported or heat is transported through the atmosphere. In the troposphere, the lowest 11 kilometers of the atmosphere, there's a lot of weather, there's circulation, you get a lot of wind, convection. You also get heat transported through radiation. So radiation, that's the way heat is transported if you're sitting near an open fireplace. When you get high in the atmosphere, in the stratosphere above 11 kilometers, there is no weather. The air is very stable, it's stratified, and so radiation is the only method of energy transport. Now, if we increase the amount of CO2 in the stratosphere, we basically are making a much bigger radiator in the upper atmosphere. A bigger radiator means that you're going to be releasing a lot more heat, and that means the air in the stratosphere will cool. Now, of course, you want there to be the same amount of heat produced from the top of the atmosphere when you have the double CO2 environment than before. So in order to get the same heat flux, to change that blue curve in the lower right curve from the -3 watts per square meter back to 0, what it was before, you have to heat or increase the temperature of the troposphere and the surface. And when you do the detailed calculations, you see the temperature plotted on the lower left. Here we have the temperature on the horizontal axis versus altitude Blue is the temperature before we double the CO2. Red is the effect of doubling the CO2. So at an altitude of about 50 kilometers, you see the temperature has gone down by about 10 degrees. So this is the stratospheric cooling. If you look near the surface, you can barely see that there's been a warming of about 1 to 2 degrees Celsius. Slide 14. So what is the change in temperature due to doubling CO2? And this is given the fancy name of climate sensitivity. Well, if you consider the water vapor to remain the same when you double CO2, everyone calculates an increase in the surface temperature of about 1.4 degrees Celsius. Now, if the temperature goes up, you would expect more water to evaporate, and you expect water vapor to increase in the atmosphere. The question is, what do the observations say? And the observations are ambiguous about whether water vapor has actually increased over the last 50 years. But let's presume it has, and let's presume water vapor has increased so that the relative humidity remains constant. If you do that, higher temperature means more water vapor. Then you see the temperature goes up by about 2 degrees instead of 1.4. Now, of course, there are a lot of other factors to consider when you consider temperature increase. The first thing I talked about was that relative humidity assumption has not been rigorously established by a long shot in the data. You also have to worry about clouds. Our calculations so far are just for the simple case of a clear sky. We have done some preliminary work, and it shows if you look at the interaction of clouds with infrared light, this is likely going to decrease the surface warming. So if you double CO2 in the presence of clouds, instead of getting an increase in temperature of about 2 degrees, you're probably going to be lower by about 25%. But in addition to heat, clouds also interact with visible sunlight. And there have been suggestions that maybe we get more cumulus clouds, which reflect sunlight more. Or maybe we get more cirrus clouds that act to trap infrared radiation more. That's unclear. Of course, if you change the temperature of the surface, you increase it, you're likely going to change your convection, your weather patterns, your ocean currents. If you increase the temperature, you could melt ice. That's going to change the reflectivity of the Earth's surface, particularly in polar regions, etc., etc. So there is considerable uncertainty when it comes to measuring temperature, and that uncertainty is represented by the IPCC reports. 30 years ago, they estimated a climate sensitivity of about 1.5 to 4.5 degrees C. After tons of work, decades of research, they still have that same temperature estimate. And the main reason is that clouds are very difficult to understand. Now let's see what's the effect of methane. So in 2019, we have about 1.8 parts per million methane in the atmosphere, CO2, 410 parts per million. If you look at the increase of methane, for the last decade, it's about 7.6 part per billion increase per year. Now, I took the 2008-2019 period because if I'd gone back to consider the last 20 years, I'd be getting a far lower number. So this 7.6 part per billion per year is really a worst case scenario. For CO2, the measurements of the last 50 years show us pretty much a steady rise of about 2.3 parts per million per year. So the important point to remember is if I take this ratio 2.3 parts per million per year divided by 7.6 part per billion per year, we see that we're producing about 300 times more CO2 than methane molecules in the atmosphere each year. Now, next question you can ask, how long does it take for to double these greenhouse gases? Well, if I take that 7.6 part per billion per year, which is very uncertain, so that's why I put it in red, and divide that into the 1.8 part per million per year, at present, we see it takes about 240 years to double methane. For CO2, we get about 2 centuries or 180 years. Now, in our calculations, we showed that there is this effect of saturation. Saturation means that CO2 is going to be much more saturated than methane. So adding one more molecule of methane is going to have a much greater effect than adding one more molecule of CO2. And that factor is 30. So if you take each methane molecule added has 30 times the effect than each CO2 molecule added, multiply it by the ratio at which you're increasing these gas concentrations, 1/300, we see we get a factor of 1/10. So the increase in temperature due to methane is only about 1/10 that for CO2. Well, we just estimated in the last slide, if we double our CO2, our climate sensitivity will increase the surface temperature somewhere between 1.5 to 2 Celsius, depending on the water vapor. If we divide that by 200 years that it takes to double CO2, we get warming of about 0.01 C per year for doubling CO2. Multiply that by 1/10, and we get warming per year for methane of about 0.001 Celsius or 1 millidegree C per year. Now, of course, these red figures have large uncertainties. I've tried to get the largest number possible. If you're looking at reality and you're wanting to see the effects, say, of agriculture, then of course you have to subtract out the industrial contribution to increasing methane. Ray Bates gave a very nice talk a few weeks ago, and I think the agricultural responsibility for methane increase is only about 1/3 or so. So this number of 1 millidegree C per year is actually going to be much less if you just look at the responsibility due to agriculture. Finally, Ireland is a very beautiful country, but it is rather small. So if you look at the number of cows blessed with an Irish passport, you're going to find a temperature estimate due to the Irish livestock extremely small. We're talking about 100 times less than that millidegree C per year. So I think, as I said 2 years ago, if you want to cut Irish livestock because you want to make a good impression on your global neighbors, that just has symbolic importance. It's not going to do anything for the atmosphere. And maybe you can instead persuade your politicians to make another symbolic action like getting rid of all cats and dogs. Slide 16. So what we've done is we've considered over 1/3 of a million different transitions of these 5 greenhouse gases. We've shown that saturation very strongly suppresses the forcings. If the methane concentration were comparable to CO2, adding one more molecule of methane would have the same effect as adding one more molecule of CO2. But because methane has 200 times less concentration than CO2, the effect of one additional methane molecule is going to be more dramatic. We have shown some very nice agreement with satellite observations. And for the technical people, we have not needed any fudge factors. The fudge factor that I'm talking about is the so-called H2O or CO2 continua. That's a fancy word, and you're probably going to ask, William, what is that? I've been asking that question, and no one seems to know. It's basically just a mathematical addition to try to get the observations to fit your model. Well, we don't need that when we fit our model to the observations, unlike other people. The surface warming that we project is 1.4 Celsius if you have constant water vapor. Water vapor will increase. We don't know how much. If you take the extreme case of constant relative humidity, which is not supported very well by observations, the surface warming due to doubling CO2 is about 2.3 Celsius. Warming due to increasing methane is going to be less than 1 milli-degrees C per year. So if there's anyone who thinks the world is going to end in 10 years due to climate Armageddon, that's nonsense. You can rest in peace or hopefully survive Corona. So Heidi should be left also in peace. Slide 17. Now what we are working on very hard is clouds. Clouds tend to scatter radiation, and this means that the mathematical equations to solve get more complicated. We're making good progress on that. And I couldn't resist seeing how well we can do, so I got some Nimbus observations for the Western Pacific. These satellite observations are shown at top. There are two curves. One is for the case of a clear sky, and the second is for the case of a cloud. Well, the clear sky curve I can model very nicely in the lower left. And the cloud curve, the plot of heat versus frequency, I've modeled on the lower right. And we think this shows very nicely what that we know what we're doing. Now, I should add to the technical people, we have not considered scattering for that lower right curve. I just considered a thick optical layer and said, what's the result of that? So the optical depth of 20, you can think of this meaning that it is very difficult for heat to get through the cloud. The cloud layer will be very thick. So we are optimistic that we can make good progress in clouds and hopefully use that to improve our estimate of forcings and temperature change, hopefully in about half a year. Finally, in this time of Corona, I realize everyone has a bit of a challenging time, and my daughter sent me the following slide, and I thought it's nice to induce a smile. Thank you for your attention.